everything, you know, I go from scratch. I also teach at Hunter College, but Hunter College I have been teaching for years. So I have a system for Hunter College, but Hunter College use Newman Learning. They use a different system. They don't use my Open Math anymore. They used to use my Open Math, but they don't use anymore. My Open Math is not as convenient as Newman Learning. Hopefully one day Brooklyn change to Newman Learning also. So there's two homework ones. There's no, just check. Okay, you see the calendar here? Is the calendar here? Yeah, I'm sorry, I'm confusing you guys. Okay, let me see if I. Yes.
I think people are confused because you said that on Friday you had a meeting regarding the homework, right?
Yes.
Before that you were giving us homework from the textbook, so I think people are confused if that homework is what we're sending you.
Okay, I see. The meeting telling me how to use, the meeting taught me how to use this calendar. How I can put like a homework 1, homework 2, exam 1, exam 2 on the calendar, and how to create homework 1, homework 2, and homework. But the meeting does not have like a unified homework sets. It's different. So no unified homework. So I have to create my own homework for you. So I tried to use the system. I try to use the system to generate questions. As you find out, some questions are very easy, some questions are very difficult. So before this class, I was trying to create homework 2 for you from the system. I just couldn't find good questions. It's even worse than homework 1. So I changed back to the test. So that's why here I wrote, so homework 2 is due on February 17th, 10 a.m. Well, maybe I change it to 10 p.m. something. Right before class, I'll change this time. Then from test on my Open Math. So choose 10 questions from this, from section 1.4, 1.5. And then send your homework to this email. All right, this is for homework 2. Let's back to homework 1. Homework 1, I choose questions from the system. All right, and before the system, I assign you some other homework on Blackboard. That's not, I'm not requiring you to send to me homework 1. No. Homework 1 on Blackboard is for your practice. Homework 1 in the system is considered as your homework 1. So now it's your homework 2. Did I make myself clear? Homework 3 will be next. So homework 1 is being repeated, right? So the first homework 1 is from the text. Then I create, because I had a Friday meeting, I create homework 1 in the system. Same material. Okay, just follow. So from now on, just follow my Open Math. I'm going to tell you homework 1, homework 2, homework 3 in my Open Math. If I could find good questions in the system, I will still do that because it's good for you. It's also good for me. If I cannot find good questions from the system, I will choose from the text. Okay, any questions? All right. So let me go to my Open Math. Let's see, homework 1. Are we talking about 2 and 3? Okay, 2 and 3. So question 2. The value of this integration may be determined by calculating the limit of a regular partitioned Riemann sum with, right, I didn't emphasize on this. But I did emphasize on the definition, remember that? So the definition of this is just this, right? So this one is to practice the definition. If it's too hard for you guys, just forget about it, all right? Just forget about it. So maybe just don't worry about it, all right? Because I don't want to spend too much time to calculate this. It's all about calculating. It's all about calculation. I don't want to spend time on that. This will tell you choose a point, right, to evaluate. 3 is the same thing. You know, it's just to understand where is the integral come from. Right? This come from, so integration is in an infinite world. Right? This long s and the dx is a pair. It's just cutting a thing into infinite many pieces. Where does it come from? It comes from taking the limit of a finite sum. Right? So coming from a finite world to infinite world. Then we take a limit. We let the piece, n piece, run into infinity pieces. So this is all about understanding the definition. And the rest is just calculation. It's a lot of calculation, so I'm not going to do here. So I don't have time for that. Oh, am I not sharing screen? I thought I'm sharing screen. Can you see it? Oh, okay. So James, if you cannot see it, just refresh. Just refresh from your end. Okay, any other questions? So if we don't answer these questions, we won't get points off. No, I'm going to fix that, all right? So don't worry about 2 and 3. But it's a good practice, you know? I'm trying to help you to really understand the integration sign, all right? Because when you do these calculations, it helps you to understand. Anyway, let me share the screen, share a new screen. Okay, so we're going to 1.4 integration formulas and the net change theorem. All right, so what does it mean, net change theorem? Okay, let's see this one, integration by a power rule, right? Let's just review. If we want to integrate from an interval from 1 to 4, the lower limit 1, upper limit is 4, that means we'll integrate this integrand over an interval from 1 to 4. So we use power rule, right? So square root of t is a t raised by half. Then the integrand becomes t raised by half plus t raised by 3/2. Then we use the power rule, right? What does the power rule? Anti-differentiation. Anti-differentiation is just total opposite from differentiation. So that's why we add 1 to the exponent, then we divide it by the new exponent, right? Then we use fundamental theorem of calculus. We find anti-differentiation, the function anti-differentiated is still a function. Then we evaluate at the lower limit, evaluate at the upper limit, then we subtract them. Same thing for this one, right? Check. So now let's see, what is the net change theorem? So net change theorem, the new value of a changing quantity equals the initial value plus the integral of the rate of change. Do you see this one? This is just rewriting the fundamental theorem of calculus, part 2, right? You see that this one is a fundamental theorem of part 1. So actually, it's just exactly, you know, I don't know why they name it net change theorem, but anyway. Let's see this one. So mathematics, we have two branches. We have one branch is called pure mathematics, which means we don't care if it can be applied in life, for life applications. So just do pure calculation. And another branch is applied mathematics. So we use mathematics to build a model for life applications. So in pure mathematics, for this area, right, if we want to find an area from 2 to 5 for this one, we would have the area of 2 to 4. We will get a positive area. Then from 4 to 5, we would get negative area. So we would get a positive area, subtract the negative area. Questions like this. Sometimes we want to find, like this. So this is from 2 to 4. What's the function? Constant function, right? The constant function is f of x equals to 40. And from 4 to 5 also is a constant function. What's a constant function? Let's say g of x or f of x equals to negative 30. Right? If we want to find the area from 2 to 5, we would split into two parts, right? We would split into two parts. So we get from 2 to 4, function is 40. Right? Then 4 to 5, negative 30. Just think of this as piecewise function, right? Piecewise function. So this function is defined as piecewise. Both. So from 2 to 4, it's a constant function of 40. From 4 to 5, it's constant function of negative 30. So we would split from 2 to 5, we would split into two intervals. So from 2 to 4 and from 4 to 5. Then integrate each one. Integrate each one. But so this is a pure math. But sometimes we want to add those two areas. You know, we want to find out the area from 2 to 4. We want to find out the area from 4 to 5. You know, we want to find the sum of those two areas. So what do? One thing we could do is we put absolute value sign. We put absolute value sign in front of it. So 40, constant 40 is already positive. So absolute value is still positive. And then constant function negative 30, when we take an absolute value, so get positive 30. In this case, we would be able to add the two areas. So the sum of the two areas we add, we get a 110. Get a 110. So it really depends. You know, it really depends on what we're looking for. Let's see more examples. So let's see example 1.24. So we want to find net displacement. So given a velocity function, v of t, so v is, represents velocity. So 3t equals 3t minus 5. So we recognize this is a linear function, right? It's a linear function. For a particle in motion from time t to 0 to time t equals 3. And we want to find the net displacement of the particle. So this, let me write in the chat. Let me write in the chat. So displacement function, usually we use s of t, if you remember that, right? It's the anti-differentiation is equals to, or let's put this way, let me put the s prime. S prime of t equals to v of t, right? We remember this, right? I wrote on the chat, I couldn't write on the screen here. So v of t is linear, so we know the displacement function is a quadratic, right? Because we anti-differentiate a velocity function, we get displacement function. All right. Oops. So we want to find the net displacement of the particle. Basically, you know, how far the particle has been moved. You know, the trajectory the particle has made. So what do we do? So from 0 to 3, we may get, if we draw the picture, we will see part of them is under x-axis. Oh, we see the figure, right? So if we draw 3t minus 5, and from 0 to 3, from 0 to 3, you know, we see we have this. We see we have anti-differentiation of this line. We will get the area of this from 0 to about 1.5. Then from 1 point, so it's down below x-axis. And from 1.5 to 3, about to 3, so it's the displacement is above x-axis, right? So if we add them, we will get positive, subtract negative, we'll probably get negative values. So what do we want to do? When we could put absolute value, we could put the absolute value in front of it, or you know what? We don't even know. We need to find out this point here. We need to find out this point. So the point between, so the point is x value comma 0. So the x-intercept. So we need to find the x-intercept. Then the x-intercept becomes a 0 to the x-intercept here, right? Then we would put the absolute value in front of it because it's underneath. It's under x-axis, so it's a negative one, negative value. And then from the x-intercept to 3 is positive. That's like a normal one. So what do? We need to find the x-intercept. We would set 3t minus 5 equals to 0, right? I couldn't write it over here. So t equals to 5 over 3, right? So you see here, if we go ahead and do the anti-differentiation, we get a negative 3 over 2. So the particle made a negative displacement. Well, that we know that's not right. So we need to find out the x-intercept. We just set to be 0. I couldn't. Oh, here. So 3t minus 5 equals 0. So t equals to 5 over 3. So this point here in between of 1 and 5 is 5 over 3. So now we can set up two integrals. We set up one integral from 0 to 5 over 3, another integral from 5 over 3 to 3. So we split the integral from 0 to 3 into two intervals, from two intervals. And we take absolute value of the velocity. So 0 to 5 over 3, because the under x value is negative, we put a negative sign, right? Put a negative sign because it's under x-axis, because it's under x-axis. So we put a negative sign, so negative, negative become positive. And from 5 over 3 to 3, that's okay. It's a positive value. We don't have to negate. Then we integrate from there, so we get in the end we get 41 over 6. So which means the particle traveled 41 over 6 meters. Okay, anyone has any questions? I think this is what they mean by net change. Net change, the total change. So we want to find out the total change. And we don't want the intervals, in between the intervals, negative and positive, offset each other. Let's see this one. How many gallons of gasoline are consumed? If the motor on a motorboat is started at t equals 0 and the boat consumes gasoline at the rate of 5 minus t cubed, cubic function, right? Polynomial of degree 3. Gasoline per hour. How much gasoline is used in the first 2 hours? So we want to find from 0 to 2, right? So we want to anti-differentiate 5 minus t cubed from 0 to 2. But if we draw this picture, 5 minus t cubed, we see part of them under x-axis, part of them above x-axis. So from 0 to 2, from 0 to 2, oh, I don't have pictures. I don't have pictures. Let me draw by hand. So actually, let me go to the whiteboard. So how do we draw? So we want to draw 5 minus x cubed. You see this, we can write as negative x cubed plus 5. Transformation, right? Transformation of x cubed. How do we draw x cubed? X cubed goes this way, right? What about negative x cubed? Let me draw in red color, in green color. If we negate, right? If we put a negative in front of x cubed, we would negate the past. We would negate negative x value to be positive. So that this is a negative x cubed, right? This graph is x cubed. Now plus 5. Plus 5. So negative x cubed is just a reflection over y-axis. Now plus 5 is what? Move up 5 units, right? So let's just pick one point. Let's see, this point is 1, 1. This point is negative 1, 1, right? So now this point being pushed up to, oh, even 0, 0. 0, 0 being pushed to be, let's see, this is 5. 5, 0, right? So my graph of that becomes somewhere like this, right? Cross, let's see. That would be difficult number to draw. Okay, so this is my negative x cubed plus 5. So I want to find from 0 to 2. Oh, that's fine. From 0 to 2. So why is 2 not ended? So we can find this point. Well, what's this point? We said this one equal to 0, right? So x equals to cubic root of 5. Well, cubic root of 5, of course, is less than cubic root of 5, right? Oh, cubic root of 5 is less than 2. And we want to find up to 2. Up to 2, maybe, oh, yes, because it's cubic root. So 2 maybe somewhere here. We do get a negative area. So that means we need to split the interval into 2 intervals. We need to go to 0, cubic root of 5, then cubic root of 5 to 2, right? We need to split into this 2. Then we take the integration. Anyone has any questions? It's always good to, you know, if we want to find, if we're in doubting of the intervals, it's good to find the x-intercept. Any questions? All right. Let's see. The book does not split into 2 intervals. The book just go ahead, did this. So from 0 to 2, I think if we do it, is the second one the same? Motorboat, I suppose. No, that's something else. Okay, I would encourage you to find out from 0, to find out the integrals from 0 to cubic root of 5. Then split into 2 intervals. Then from cubic root of 5 to 2. Okay, it should be different. It should be different. But I don't have time to do the calculation, and I don't want to do the calculation for now. Maybe later when I have time, I'll do that. Okay, let's keep moving. So this one, we have piecewise function, right? A piecewise function, like the first one. So t in between 0 and a half is defined as a linear function, 20t plus 5. In between of half and 1 is defined as constant function, 15. And what do we want to do? We want to, so the velocity function, so his speed is this, right? Velocity function usually measures the speed of a particle or speed of a person, or speed in this case ice boating. So for the second half hour of the engines outgoing, the wind remains steady at 15 mph. So this first half is a linear function, 20t plus 5. Second half is a constant function. Now, recalling that the engines iceboat travels at twice the wind speed. Twice the wind speed. So this is the wind speed. So the v of t is the speed of wind. But the Andrew travels twice as much, so it's 2 vt. So it's 2 times vt. Assuming he moves in a straight line away from his starting point, how far is Andrew from his starting point after 1 hour? Okay, so we need to find from 0 to 1 hour his, the distance he traveled, right? So which is anti-differentiation of v of t. So integrals of v of t from 0 to 1. But because we have 2 functions, so we have to split into 2 integrals. Because he travels twice of the wind speed, so we have this 2 times v of t. So distance he traveled equals the interval from 0 to 1, 2 of the wind speed. And from 0 to half, we have a linear function 20t plus 5. From half to 1, we have a constant function 15. So, the rest is just a calculation, right? Anti-differentiate 40t, we get 20t squared. Anti-differentiate 10, that's just 10t.
Professor,
then we want to evaluate.
I'm sorry.
Yes.
I assume that 1/3 is a typo on the second line.
1/3.
1/3.
Hold on a sec. 1/3.
On the second line. This is the second.
Oh, yeah.
Limit.
You're right. That's typo.
Okay.
That's typo.
Okay, thank
Right.
you.
That's typo. That's 1/2. I didn't even see it. Thank you. No. So anti-differentiate 30, that's 30t. Then we evaluate from half to 1. The rest is just calculation. So in the end, we get 25. So this is a piecewise function. Okay, you may try this on your own when you have time, because both are linear functions. Okay, now something. How do we integrate even and odd functions with the lower limit and the upper limit are additive inverse? You see, in this case, the lower limit is -a, the upper limit is a. So they are inverse with each other, right? Those two are additive inverse, which means a plus -a equals 0. So whenever we see something like this, lower limit and upper limit are additive inverse, we think, okay, if the integrand is an even function in this case, if the integrand is an even function, we can change it to be 2 from 0 to positive a, then integrate, just double the integration, which means that's a perfect symmetry. Perfect. Just imagine f of x equals x squared. Right? Just imagine or draw on your paper. Imagine we have a quadratic function. F of x is a quadratic function. If we go from -1 to 1, you see that's a perfect symmetry, right? So from -1 to 0, the integration is exactly the same as the integration from 0 to 1. So that's why we can split we can see, okay, that's exactly, I can find half of it from 0 to 1. So I don't have to deal with the negative numbers. And then I just double it. Okay, and it's most useful for the integrand to be odd function. Because some integrands are very, very annoying. But whenever, so actually in your test, if you see the integrand is so annoying and the lower limit and the upper limit are additive inverse, all you have to check is to check the integrand is an odd function. If the integrand is an odd function, you get 0. Because why? Because if we integrate odd function, after integration, it becomes an even function, right? So when we subtract, the negative a part will give us exactly the same value as the evaluation for a. So subtraction just gets 0. All right. You can think of odd function, right? You can think about the odd function. So this is a pure mathematics. And now we're not talking about net change. Now it's different from the talking about find a displacement or find a distance. Find a distance, find a displacement, that's applied mathematics. Here we're talking about pure mathematics. Okay, pure mathematics. So we don't consider the net change. So we just apply both. So if integrand is odd function, lower limit and upper limit are additive inverse with each other, so we get 0 right away. Right? We don't have to do any calculation, but we just have to have a good eye to recognize f of x is odd function. Okay, let's see some examples. So this integrand 3x raised by 8 minus 2 is even function, right? I hope you remember the definition of even function. Let me just remind you, type in this chat. So even function means if we input negative x into the function, that equals to input f of x. So f of negative x equals to f of x. So one example to remember is just x squared. Right? If we input negative x, then we square it, negative x times negative x, still x squared. Okay. So this is even function. And by the theorem here, we just do 2 times evaluation from 0 to 2. Right? We just change to be from 0 to 2. Hold on a second. Yeah, from 0 to 2, right? Then we double it. We multiply by 2, right? We get 1,000 divided by 3. But if we do integrate everything, we still get the same thing, 1,000 divided by 3. So for this typical one, right? 2 ways, we get the same answer. Any questions? All right. So as I said, most useful for the integrand to be odd function. Because it is an even function, that's a perfect symmetry. Let's say odd function. So evaluate the definite integral of odd function -5 sine x over the interval from -pi to pi. How do we know sine x is odd function? We could think about sine of -x. I'm typing in the chat. That equals negative sine x, right? That's why it's odd function. So sine x is odd function. From -pi to pi, well, -5 is just a scalar. So sine x is odd function. So the integrand is odd function. We don't have to calculate. Just equal to 0. Okay, just by the theorem equals 0. If we do the calculation, calculate in the end, we get 0. And the graph is like this. Again, this is what talking about pure mathematics. Okay, pure mathematics. So from negative pi to pi, this is the sine curve, right? Sine curve. So under the sine curve, we see from negative pi to 0, get the area above x-axis. From 0 to pi, we get an area below x-axis. Oh, that's a 5. That's positive 5. Negative 5. No, that's negative 5. This is type O again. This is a negative 5 because this is already been reflected over x-axis. So this is a negative 5 sine x. So will you ask us to evaluate or just recognize the odd function? You could do both ways, but when I give you a question like this, the integral will be very difficult. You know, you won't be able to integrate easily. So if the function is odd, it always equals to 0. If the function is odd, the upper limit and lower limit are additive inverse. That means you add the lower limit and the upper limit, you get 0. You see negative pi to pi, a to negative a, all right? So lower limit and upper limit are additive inverse. If the integral is odd function, you get 0. Yes. So if I ever give you a question like this, the integral will be very difficult to do it. Actually, I want to show you one. Let me see if I can find it. Let me see, still here. Okay, still here. So let me show you one question. It doesn't pop up. Hold on a second. Let me get it again. Let me leave this one. Let me leave this open. Doesn't share my email. Mail. Oh, let me see. Let's see. Interesting. Doesn't share my email. Why not sharing my email? Yeah, it doesn't show to this screen. Doesn't show. Basically, let me read to you what's the integral. So integration from -2 to 2, the integral is this. It's x cubed times cosine x over 2 plus half, then multiply by 4 minus x squared, then dx. So 4 minus x squared is a positive part. It's an even part of the function. Cosine x, well, cosine x over 2 is an even function. So sine x is odd function, but cosine x is even function. X cubed is odd function. So if we have an odd function times the even function times the even function, we still get an odd function. So in the long string of functions, as long as we detect one, you know, we have odd number many part to be odd functions. So the whole function is an odd function. So in this case, there's no way you can integrate this, you know, not using a calculator. There's no way to integrate by hand. So in that case, we just use this theorem. We say, okay, the integrand is odd function. So the upper limit and lower limit are additive inverse. So the integration just equals to 0. Odd x, odd even. Okay, let me write here. Let's see if I have f of x times g of x times h of x, right? I have a bunch of functions, right? So let's see here, if I have 3 functions, if one function is odd, the other two are even, or neither, the other two are even, so the whole f times g times h will be odd. If if f and g are odd functions, h is an even function, the whole thing is an even function, right? Just like adding the exponent. Okay. All right, so pure mathematics, those two areas just cancel each other. But if we're talking about in life situation, it would be different, right? If we talk about displacement, if we talk about the trajectory a particle has made, it will be different. So same thing for this, right? Or this one we can do it. This one we just do 2 integration from 0 to 2 x raised by 4. All right, so that's 1.4. Now let's go to 1.5. Substitution is our it's the main topic for today. All right, so now let's see this one. So we have integration. Can you see my cursor on the screen? Yes? Okay, great. If you cannot see it, that would be bad. All right. So here we want to integrate x squared. So integrate x squared minus 3 raised by cube times 2x dx. So this is an infinite integral, right? So we don't have a lower limit, we don't have an upper limit. So if we don't have a lower limit, we don't have an upper limit, the integration would be a family of functions. We just add c in the end. So here, let's recognize. So if f of x equals to x cubed, gx equals to x squared minus 3. And we see this in x squared minus 3 squared is composition of two functions, right? It's f composed with g, right? It's f composed with g, or f takes g as the input. Then what's 2x? 2x, we see that's g prime of x. That's g prime of x. So in this case, we say, okay, if I anti-differentiate x squared minus 3 raised by 3, right, I would do 3 plus 1, then divided by, so I would raise the exponent by 1. I would have x squared minus 3 raised by 4, then divided by 4, and then I have to consider my derivative, 2x, and bingo, right here, 2x. So what do? With this, we use u substitution. We said, okay, let u be x squared minus 3. Well, let me not get ahead of myself. So let u be g of x, where g prime of x is continuous over the integral. Let f of x be continuous over the corresponding range of g, and then let capital letter of f of x be an antiderivative of x. Then we have this. So the integrand we recognize as f composed with g, then g prime, or just f of u du. So g prime of x dx is our du. And f takes g, f composed with g, that's our f of u. All right. So when we anti-differentiate this, so the lowercase f is a derivative of the capital F. So we get anti-differentiation of little f, which is big F, plus a constant. So anti-differentiate an infinite integral, we get a family of functions. So this c can be any constant number. Get a family of functions. So let's just see examples. So this, this might be a little bit confusing. We don't need to go through the proofs. Let's see some example. Oh, let's see this example. All right. So the integrand is x squared minus 3 raised by 3. Then du is 2x dx. So what do? So we do this. We said let u be x squared minus 3. So basically you see u is a function of x. Then we take a derivative of du. You know, how do we take a derivative of du? We see du dx equals to 2x. But somehow for the anti-differentiation, we write this way. We write du dx, du divided by dx. We don't write it that way. We write dx on the other side. We write du equals to 2x dx. This is exactly the same as du divided by dx equal to x, right? But for integration, we write this way. We write du equals to 2x times dx. So 2x dx is our du. 2x dx is our du. And x squared minus 3 is our u. So now we change the variables to be u. So the convenience of this is after we do this, we can use power rule. So u cubed anti-differentiate, we get u raised by 4 divided by 4, right, plus c. Where did the cube on the u come from? If the one has, this 3 is here. They read 3 too high. It's way above, right? It's way above, yes. Remember in the beginning? Let me go back to this so you can see clearly. Right here, you see this one, the integrand, right? The integrand is x squared minus 3 raised by 3. But for this one, somehow, it's just too high above here. Okay. You're welcome. Questions are always good. So you see, now we have integration u cubed du. Now use power rule. U raised by 4 divided by 4 plus c. Okay. All right, let's see more. So then, of course, we have to substitute u back. What is u? U is x squared minus 3. So the anti-differentiation of that is a family of functions. So this is not definite integral. Definite integral, we can use fundamental calculus of part 2 to evaluate to be a number. But this one, we don't have a lower limit, we don't have an upper limit, all right? So this is an indefinite integral. So we get a family of functions. Just u du. Okay, let's see this one. So we want u to be 3x squared plus 4, right? Then we take a derivative of u. So du dx, exactly 6x, right? So 6x dx would be our du. And the integrand, this is 3x squared plus 4 raised by 4 will become u raised by 4. So we let u be 3x squared plus 4. So du over dx will be 6x, but we write as du equals 6x dx. Then we substitute our variable. 6x dx becomes du, and 3x squared plus 4 raised by 4 becomes u raised by 4. Power rule, we get u raised by 5 divided by 5 plus c. Substitute the u back. U as 3x squared plus 4, right? So we get 3x squared plus 4 raised by 5 divided by 5 plus c. Not so difficult, right? Anyone has any questions? So this is u substitution. Well, let's see this one. We would let u be x cubed minus 3. Then du dx will be 3x squared, right here, right? Then we'll just change 3x squared dx to be du, and x cubed minus 3 to be u squared. Then we anti-differentiate, right? We have u cubed divided by 3 plus c. Then we change u back to be x cubed minus 3. We will get x cubed minus 3 raised by 3 divided by 3 plus c. Can we try an example on our own or no? Sometimes I was worried about, we will do this later on after I finish this, okay? We will do some of them. sometimes I worry if I don't have enough time to cover the material. Okay, let's see this one. This one we have square root of z squared minus 5. We can write that one as, so let u be z squared minus 5, right? Then du will be 2z, right? dz, 2z dz. And we don't have 2 in the integrand. So what do? We offset with half, right? Or we can write z dz, because here we have z dz. So we just divide by 2 on both sides. So we write du divided by 2 equals to z dz, right? Then we change z dz to be du over half. Then we have u square root of u. Or square root of u is just u raised by half. Right? So let u be z squared minus 5. So du equals to 2z dz. And we don't have 2 in the integrand, so we only have z dz. So we divide by 2 on both sides. So z dz equals to half du. Then we can substitute. So substitute z dz with u divided by 2. Well, divided by 2 is half. So we can pull out the integration sign. Then square root of u is u raised by half. Now we can use power rule. So we got u raised by 3 halves divided by 3 halves. Right? We still have this half to multiply and plus c. Then we change u back to be z squared minus 5. So we have 1/3 times z squared minus 5 raised by 3 halves plus c. All right. So that's a u substitution. Okay, you know what? I'd like to try this. I give you 3 minutes to try 1.26. So I'll get some water for myself.
Okay, guys, she's gone.
Let me try myself also. Okay, if you have a solution, type in the chat. X raised by 3 plus 5 raised by 10 divided by 30. Yes, Then add c to it. Yes, add c to it, because this is an indefinite integrals. We get a family of functions depends on c. Okay, great. Anyone has any questions? All right. Yeah, 1 over 30 x cubed plus 5 raised by 10 plus c. Yes. Why over 30? Because we want to let u, let me type in the chat. So u, we said u equals x cubed plus 5. Right, then what's du? du equals to 3x squared dx. But we don't have this 3 in the integrand. So what do? We write du divided by 3, or 1/3 of du equals to x squared dx. And so that's 1/3. But when then we substitute x cubed plus 5 into u. So we have u raised by 9. So when we anti-differentiate u raised by 9, what do we get? We get a u raised by 10 divided by 10, right? 1/10. So we get a 1/10 of this. 1/10 multiplied by 1/3, that's 1 over 30. Does that make sense? Okay. All right. So make sure in the beginning, do step by step. All right. Once you become good at it, you can skip some steps. Now let's use u substitution for trigonometry functions. So in this case, we want to let u be cosine t, right? Then derivative of cosine t, so we will have du equals to negative sine t, which we see here. We have sine t dt. We just don't have the negative sign. The trig functions. So we set u equals to cosine t, then du equals to negative sine t dt. So we don't have negative sign, right? We just read the negative du. So our sine t dt equals to negative du. So negative sign, -1, we can always put up front in front of the integration sign. So we have 1 over u cubed, right? This is u raised by -3. We can also use power rule. So u raised by -3, we add 1 to it, divided by the new exponent with -2. So get negative half, u raised by half, u raised by -2 plus c. We change u back to be cosine t, right? Negative become positive. So u raised by -2, that means u in the denominator. So u squared in the denominator, or u is cosine t. So in the end, we get 1 over 2 cosine squared t plus c. Right? This is deal with trig functions. Any questions? Okay. All right. I give you 3 minutes to try this one, 1.27. What do we have? Let u be sine t, cosecant. Oh, okay, yes. Because 1 over sine is cosecant. Damon is right. U equals to sine t, then du, right? Du equals to cosine t dt. Okay, du equals cosine t dt, just du divided by dt equals cosine t, right? Negative, you're right. Oh, Damon missing the negative sign, yes. Yeah, Damon, you're missing negative sign because we have sine raised by -2. Add 1 to it, -2 plus 1 is -1, so we have to divide by -1, so we get a negative sign. Yes, okay, anyone has any questions? All right, let's keep moving. Okay, let's see this one. So let u be x minus 1, then du equals to dx. But this does not account for the x in the numerator of the integrand, right? So we need to express x in terms of u. So if u equals x minus 1, then we can write x equals u plus 1. Okay, this is something different now. So we need to rewrite x because we want to substitute x into u. So we let u be x minus 1. We need to also substitute this x in the numerator. So then x equals to u plus 1. So now we can substitute x into u term. So x is u plus 1, and denominator is the square root of u. Right? We can divide u divided by square root of u. That's just square root of u, right? That's just u raised by half. Well, 1 over square root of u is u raised by -half. Now we can use power rule and the differentiation power rule. So we add 1 to the numerator, add 1 to the exponent, divided by the new exponent. So get those two. Then we change u back to be x minus 1. To be x minus 1. In the end, after calculations, we get this. Okay, let's go back a little bit. So the difference from before is we see we have x in the numerator, we have square root of x minus 1 in the denominator. So we want to use u to substitute x minus 1. Then we have to substitute the x in the numerator too. So the x in the numerator substitute to be u plus 1. So this is a crucial step. The rest is just calculation. Anyone has any questions? All right, let's keep moving. Checkpoint. Okay, this is similar to before, right? Okay, I give you 2 to 3 minutes to do this. So I'm going to do myself also. So basically it was -5, you would add 5. What do you mean? Damon, what do you mean by that? It was -5, you would add -5. Oh, you mean if I have u equals to x minus 5 here? Of course, if u equals to x minus 5, my x will be u plus 5, right? I just rewrite this equation. Yeah, just rewrite this equation. You're right. Okay, this one, okay. What do we have? Negative, like quarter cosine. Ali, what do you miss? You're missing something. Damon, you're missing something. You guys are right, but you're missing, right, you're missing plus c. Yes. Yeah, the variable, right, variable x also. Okay, great. That's it. Anyone has any questions? Negative, right? Golem? Negative. Yeah, negative cosine t raised by 4 divided by 4 plus c. Okay, yes. All right. Okay, now we want to do substitution for definite integrals. Okay. For indefinite integrals, we get a family of functions because we have to add c to it. We have to add c to the anti-differentiation of the integrand. But for definite integrals, we get a number, right? Let's see some examples. So in this case, this is saying from A to B, and we want to write the lower limits. So this is called changing of the limits, but we don't really need to change the limits because changing limits sometimes confuse people. So this one is not so important. Okay, change the limits is not so important because we can always change it back, right? We let u, we let u be one thing. In the end, when we finish, we can always change u back to what we have. So we don't have to really have to change the limits. So this one is saying, we can change the limits, change a to be function of a, change b to be function of b. No, we don't have to do that. But in the middle, we want to use u substitution. So one way is you can change it to be u, you change the lower limit, upper limit to be a function of a and b, then you can calculate it from here. You can calculate from here. So what do you get? Let me write in the chat. Then if you evaluate from there, you get f of g of b subtract f of g of a. Right? If changing limits doesn't confuse you, you can go this way. Because go this way is faster because we don't have to change it back. But if this way confuse you, because I always find some students get confused by this, you don't need to change the limits. Okay, let's see examples. Let's see this one. We want u to be 1 plus 2x cubed, then du equals 6x squared dx, right? And of course, we don't have 6 in the integrand, so we have x squared dx, which is substitute x squared dx into du divided by 6. Or we can put 1 over 6 up front the integration sign. Right? So we change this one to be 1 over 6, right? 1 plus 2x cubed raised by 5, which is to be u raised by 5. X squared dx is 1 over 6 du. You see here they change the limits, right? So from here, x goes from 0 to 1. And u equals to 1 plus 2x cubed. So one way is we can calculate u of 0. So what's the u of 0? U of 0 is 1, right? And then we can calculate u of 1, because u is a function of x. Think about u of x. So when x equals to 1, we get 3. You see here, they change the limits to be 1 and 3. This is one way of doing it. And we don't really have to do this way. We can change u back. All right, we can change u back to be 1 plus 2x cubed. But if we don't, so we get 1 over 6, the integration from 1 to 3. The integrand is u5. So power rule for anti-differentiation, we get a u raised by 6 divided by 6. Then 1 over 6 of it, we evaluate it from 1 to 3. So we get 182 divided by 9. So this is one way of doing it. If you don't want to change the limits, you can substitute u back, right? We integrate this, we have u raised by 5 divided by u raised by 6 divided by 6. So basically 1 over 6 times u raised by 6 divided by 6, that's u raised by 6 divided by 36. Then u is 1 plus 2x cubed. So then we can still evaluate x from 0 to 1. Okay. Excuse me. Okay, anyone has any questions? All right, let's see. 21, okay, we have some time. Okay, let's try this, 1.29. I'm going to try myself also. All right, let me know what you get. Okay, what do you get? I get negative 1/24. So u equals to 2y squared minus 3 du equals to 4y dy, and I rewrite it as 1/4 du equals to y dy, because in the integral I only have y dy. Then when I integrate, I get u raised by 6. I get 1/6 divided by stuck. So 1/4 times, excuse me, times 1/6. Hold on, let me see, where do you stuck? You have negative 1/4. Why negative?
I forgot to I forgot to apply the power rule. Sorry, I'm not done yet. I was
Oh,
not
you're
done.
not there. Okay, so I get 1/4 times 1/6 u raised by 6. Right, so after anti-differentiate, that's 1/24 u raised by 6. Then I want to change it back. That's 1/24. Well, what's my u? That's 2y squared minus 3 raised by 6. Oh, hold on, I did something wrong. I forgot to change back to that. So now I want to evaluate this at 0. If I had 0, I get 1/24 times negative 3 raised by 6, right? At the -1, I get a 1/24. On y squared, -1 is still 1. I have 2 minus 3, which is a -1 raised by 6. So -3 raised by 6, oh, that's a big number. -1 raised by 6, that's just, 1/24. Then 1/24 times -3 raised by 6, that's just 3 raised by 6. So I don't want to do the calculation. I got a 1/24, 3 raised by 6 minus 1. -1/6. Okay, let's see. 2y squared minus 3. Let me write 2y squared minus 3 raised by 5 y dy goes from -1 to 0. Let's go to the whiteboard. Let's do this together. So -1 up to 0 of y times 2y squared minus 3, 2y squared minus 3, oops, raised by 5 dy. Let's use u substitution. So let u be 2y squared minus 3. Right? Then du equals to 4y dy. Right? The same thing as du divided by dy, derivative of u, right, equals to 4y. You see here, if we want to change the limits, you see u is a function of x. I see. Okay, let's check. So u just x, right? U is a function of not x, y. U is a function of y. Usually we use the notation of du dy, right? Usually we write it as du dy. But let me just write it here to make sure everyone understands. So du, we write du over dy, or sometimes we use the notation u prime derivative of function of u, or we write as du dy, right? But we can also write as du on one side, dy on the other side. So this equals to 4y. Then we can, so we don't have 4 in the integrand. We only have y dy. So we divide by 4 on both sides. So that dy divided by 4 equals to y dy. Is it 91/3? Let's check. Let's check. So now we can substitute, right? So it goes from -1 to 0. Let me change my color. You see I have y times dy. That's my du divided by 4, right? Divided by 4, I'm going to write here up front. So I have du, right? So y dy becomes du divided by 4. And this inside, this is u raised by 5, right? This is u raised by 5. If I want to change the limit, I also can change the limit. I can evaluate u of -1. What's u of -1? 2 times -1 squared. That's 2 times -1 squared is 1. 2 times 1 is 2. So 2 minus 3, it just equals -1, right? Then I can evaluate u of 0. u of 0 is -3. Right? So if I want, I can evaluate it from here. I can change those two. I can change -1 to be, or -1 doesn't change, still -1. But u of 0, so this has to be u of 0. Let me to be exactly correct. So this has to be u of 1, -1. Because here, this is the x value, right? This is for, not for x, for y. This is saying y equals -1. This is saying y equals 0. But when I substitute into u, I could change the limits. If this confuses you, forget about it. If it doesn't confuse you, you can change the limits here. You can find u of 0, u of y, right? U of 0, u of -1. Use this substitution. So I calculated u of -1, still -1. So I still have this -1. And u of 0 is -3. Right? So anti-differentiate. I got 1/4 times u raised by 6 divided by 6 power rule. Then I evaluate from -1 up to -3. Right? 1/4 times 1/6, that's 1/24. Then let's do a calculation. U raised by 6, -3 raised by 6 is the same as 3 raised by 6 because of even exponent. Minus -1 raised by 6 is just 1. So 3 raised by 6 minus 1. Well, that's too big number. What's 3 raised by 6? 3 raised by 3 is 27. That's 27 times 27. Okay, I don't want to do a calculation. So basically it's 1/24, 729. Thank you. So 729 minus 1. So 728 divided by 24. Well, that can be simplified because both, right? So I can divide it. I can do, simplify to be 91/3. Thank you so much. Great. Anyone has any questions? All right, pretty good. Do you have to plug in the bonds into U? Okay, Ali, that's a very good question. I forgot to mention that. So 2 ways of doing this. One way is we change the limits. So here the limits is regarding Y. When we do a substitution with U, we also change it to be function of U, function of U. Another way is we don't have to do this. Okay, another way is once we have this, we go back, right? Let me write here. So we get a 1/24. We change U back to be 2y squared. 2y squared minus 3 raised by 6. Evaluate at the original limit, -1 to 0. All right. So we don't have to change the limits if we get confused by this. We just change U. We just change U back to be, it's a substitution. Right? 2y squared minus 3. Then we evaluate from here. All right. Okay, great. Any other questions? Okay, let's keep going. Okay, let's see this one. So the E, we have E term. So we would want the exponent of E to be U in this case. So we want u, whenever we see e term in the integrand, we want u to be the exponent of e. So u equals 4x squared plus 3. Then du dx is ax, right? It's ax. And we can change the limit, right? When x equals 0, if x equals 0, we see u equals 3. Right? We just plug into this. When x equals 1, u equals 7. So we could change the limits to be 3 to 7. The x dx, we see the du divided by 8, right? So we can pull out 1/8 up front. So we get 1/8 from 3 to 7, anti-differentiate e to the u. Well, e to the u, anti-differentiate e to the u, it is itself. It's e to the u, right? Then we just do the calculation. This is 1/8 e to the 7 minus e to the 3. And this is a perfect answer. We don't have to evaluate. We don't really have to approximate, right? So e to the 7 minus e to the 3 divided by 8 is a perfect answer. Any questions? All right. Okay, let me see how many we have. Thank you. Oh, exercise. Okay, great. Let's do this. Let's use 3 minutes to do this. So I'm going to give you a hint. Let u be the angle of cosine, all right? So cosine followed by angle. Let u be pi over 2 x cubed. Go from there. Figure out the du dx. Then substitute. Okay, get a negative 2 divided by 3 pi sine 1. Oh, no, I did it wrong. U of 0 equals 0. U of 1 equals pi over 2. So this is pi over 2. U of 0 equals 0. So this is pi over 2. So sine pi over 2 minus 0. Actually, 2 over 3 pi. We got 2 over 3 pi. Positive, right? Yeah, my first answer was wrong. I just saw my mistakes. So my second answer is 2 over 3 pi. Let me see again. So I let u be pi over 2x cubed. Then u of 0, that will be 0. Then u of 1 will be pi over 2. So I change my limit to be 0 to pi over 2. So x squared dx is, so u equals pi over 2x cubed. Du would be 3 pi, 3 times pi over 2. That's 3 pi over 2 x squared dx. So x squared dx, I multiply 2 over 3 pi on both sides. So x squared dx equals to 2 over 3 pi du. Then I substitute. So I get 2 over 3 pi, integration sign, 0 from pi over 2, cosine u du. Cosine u anti-differentiate, that's sine u. So I evaluate from 0 to pi over 2. Sine 0, that's 0. Sine pi over 2 is 1. So I get 2 over 3 pi. Paul got -1. Well, let's bring to the whiteboard. Any other answers? -2 sine pi over 2. What's sine pi over 2? What's sine pi over 2? Sine pi over 2 is 1. So we let u equals to pi over 2 x cubed. Then du equals to 3 pi over 2 x squared. That is x squared. Okay, I see. X squared dx equals to 2 over 3 pi du. So then we substitute. All right. So with this, oh, also I can calculate u of lower limit. Lower limit is 0. So u of 0 is just 0, right? Because x is 0, pi over 2 times 0 is just 0. Then I can calculate u of 1. You see u of 1, the x cubed, 1 cubed is 1, so that's pi over 2. So now I can, so this is constant. I can write up front, so 2 over 3 pi. Okay. Then inside becomes cosine u du, right? So when then my lower limit becomes still 0. My upper limit is pi over 2. Yes, Paul, you have the same answer as me. Right? Anti-differentiate cosine, that's sine, right? So 2 over 3 pi. Anti-differentiate cosine, this is sine u. Then we want to evaluate from 0 to pi over 2. Right. So 2 over 3 pi. You get a sine pi over 2. Well, what's sine pi over 2? Beautiful value, right? 1. You have to know that. What's the sine 0? 0. Right. So, which is in the end, which is 2 over 3 pi. Anyone has any questions? You're welcome. All right. Hopefully, some of you are very quiet. I don't know if you get or not. If you still get if you get confused or something, there's a lot of YouTube to watch. Okay, YouTube is a good place to consult. And yeah, and also please try your homework. All right, I assigned the homework. You only need to submit to me 10 questions, but you should finish all the questions, because the future exams will be choosing. The future exam questions will be choosing from those questions assigned to you. Okay. All right. Thank you. Have a good night. If you have questions, I'm still here.